All right, let's get started. Is this on? Yes, it is. Perfect. All right, so we're going to start with titrations today, where we left off last time, the last topic of chapter 14. All right. So remember from last chapter, chapter 14, the structure of the chapter was like this. You had a bunch of pure substances whose pH you needed to find, right? We had strong acids and strong bases. We had weak acids and weak bases. And then we had the conjugates, pH of salts, just salt. And then we moved on to mixtures, right? Taking those elementary substances and combining them. And the first mixture that we learned about was a weak species with its conjugate, which is usually present in the form of a salt, right? That mixture we call buffer. And today we're going to be talking about the final mixture, which is a weak species with a strong species. And if one's acid, the other one's base. If one's base, the other one's acid. This is titration, aka neutralization. Right? Acids and bases are opposites of each other, and if you combine them, they neutralize. So titrations is just a fancy name for neutralization. Okay. And there are only 3 possible questions from titration. And they're very easy. So you have a strong and a weak substance, right? What are the 3 possibilities that can happen? You can have more strong than weak. You can have more weak than strong. Or you can have the same amount, right? So we'll work with those 3 questions in parallel to highlight the similarities and the differences between the 3 types of questions. So here's a question. 500 milliliters of a 0.1 molar NaOH solution is combined with or titrated with 300 milliliters of 0.2 molar acetic acid, CH3COOH. Calculate the pH of the resulting solution. Let me make this 0.3. The NaOH, change that from 0.1 to 0.3. Okay, so that's the first question. The second one is exactly the same, except I'm going to swap the NaOH and the CH3COOH. So this time you had 500 milliliters, 0.3 molars of acetic acid combined with, 300 milliliters of 0.2 molar NaOH. And then lastly, we need them to be the same, right? So lastly, let's just do 500 milliliters of 0.3 molars CH3COOH. In fact, I'm not even going to give you the amount of NaOH. I'm just going to say titrated to equivalence. Titrated with NaOH to equivalence. Okay. Yes. This one? Of the resultant solution. Yeah. And the questions are the same. I'm just changing around the values. Okay. Now, the main thing to remember is that in a reaction, anytime you have a strong substance to work with, like a strong acid or a strong base, the reaction will go to completion. That means that one of the reaction will go as far as possible until one of the reactants run out. Okay? The limiting reactant, until it runs out, the reaction will proceed. So that's the key thing to note in titrations, because of the presence of a strong species every time. So what do we have here? We have NaOH that reacts with CH3COOH to give, well, water, because the OH and the H combine to form water. And what else? Oh, the broken pieces, right? Salt is formed from the broken pieces. So what's left over here? Na. What's left here? CH3COO. There's your salt. CH3COO-Na. Just to say, yes. No, but this is convention. You can write NaCH3COO, that's fine. Yeah. Be careful because, for example, if I was doing barium hydroxide with CH3COOH, then of course I get water, but look at what's left over here. There's a Ba2 plus, and here I've got the acetate, CH3COO minus, right? Now there's a charge mismatch. This has a 2 plus charge, this has a 1 minus charge. Unlike here, where both of them had the same, this is plus 1, this is minus 1. So I could just combine them. Here you need to do the crisscross. 2 and 1, right, to figure out the proper formula of the salt. So Ba1, CH3COO twice. Okay? If there's a charge mismatch, do the crisscross thing. Crisscross is not important if both are 1 because 1 crisscrossed is still 1. Okay. Now back to this question. Remember from last time, anytime you have two solutions that are mixed together, things become complicated, right? Because the molarities change. The initial molarities of 0.3 and 0.2 change to something else in the combined solution. And what goes into the ice table are the combined molarities. So if you can do M1V1 equals M2V2 and all that analysis that we did last time. However, the easier route is to work with millimoles, right? Millimoles is just milliliters times molarity. So 0.3 times 500 is what? 150. So this is 150 millimoles. And so ice tables work completely fine with millimoles or molarities. It doesn't matter what you use. Okay? But as soon as you're done with the ice table, all the subsequent calculations, you want to convert the millimoles back to molarities at the end. That's easier than doing it here. We'll get to that in a second. This is, what is it? 0.2 times 60. Water, I don't care. 0 to begin with. So this is an ice table. Change minus x plus x. So 150 minus x, 60 minus x, and x. So what do we have? Oh, Here's the thing. This is a perfectly fine ice table, except that we don't need to solve for x. We already know what x is, because we know the fact that these reactions go to completion because there is a strong substance present. So let's take out the x's and write down what it should be. Which one's limiting here? Which one's going to run out first? This has 150, this has 60, and it's 1-to-1 ratio. This one's going to run out first, right? Because it's present in a lower amount. So all of that is going to get used up. Negative 16 millimoles, negative 16 millimoles, and positive 60 millimoles. So at the end, 150 minus 60, I have 90 millimoles of NaOH that survives. I have 0 millimoles of CH3COOH that survives. And I have 60 millimoles of the salt thing that survives. Okay, so this was a strong base, weak acid, and salt. Look at what survives at the end once the neutralization has happened to the extent possible. Ooh, shit. All right. We're going to continue at a possible risks to our lives. It's fine. All right, so there's a strong species that survives. There is a salt that survives at the end, and obviously there's water, but we don't care about that. Now, here's another thing to note. Does the salt affect the pH? Does it have anything that's not neutral? This is neutral, right? Because Na came from a strong base. Conjugates of strong species are neutral. This is neutral. This came from a weak acid, so this is basic. This actually does affect the pH of the solution. This is pH active. However, because it's being paired with a strong base, the strong species, if it survives at the end, it dominates. So you can pretend like this doesn't even exist. It does affect the pH just a little bit, but you can ignore that because a strong species survives and it dominates. Okay? So I forgot to say this. There's nothing new in titrations. Each of these cases boil down to one of the cases that we have studied before. What does this case boil down to? pH of a strong species. The first topic that we studied in chapter 14. That's all it is. We don't care about the salt. All we have to do is to calculate the pH of 90 millimolars of NaOH. Great. Let's start by calculating its molarity. 90 millimoles. What is the total volume of the solution? Looking at the question. Say that again. 800, right? You have a 500 milliliter solution combining with 300 milliliters, so that's 800 milliliters. Divide that, 90 divided by 80. Should be a little over 10. Yeah, can someone do this on a calculator, please? Yeah. Say that again. Oh, it should be 800, you're right. Okay. Usually to calculate molarities, we divide moles by liters, right? It's equivalent to dividing millimoles by milliliters. Because look, the millis cancel, and what do you have? Moles divided by liters. So it's the same ratio. All right, what is this? 0, say that again. 100? 112. Okay. Molarity, great. So the question now is calculate the molarity of 0.112 molar NaOH. Okay, how do we do this? From the first topic, NaOH is a strong species, so it completely breaks down into Na plus and OH minus. So if you start with 0.112 molar, all of that get consumed and gives you 0.112 molar Na plus and 0.112 molar OH minus. So what can I calculate using this value? POH, good. Which is negative log of 0.112, which is some number. And so pH, the last dance that we always perform for bases, 14 minus. Yes?
Can you explain again how, like, the CH3COO, it's a base because it comes from a weak acid, right?
Yeah.
So then why is it
Being ignored?
Yeah.
That's just because it's a very good approximation when you have a weak species present with a strong species to completely ignore the weak species.
Wait, that's a weak base?
Yes, conjugates are almost always weak.
Okay, so conjugates would never be like a strong.
Yeah. If you have an explicitly strong species like this, that dominates. Everything else, it overpowers. Yeah.
Could you explain why for the ICE table,
Yeah.
the ICE table, why we didn't have to like solve for X?
Solve for X. You solve for X if the reaction only doesn't go to completion. If the reaction only goes part of the way through, right? In the case of weak species, they only partially dissociate into H plus or OH minus, depending on if it's acid or base. Remember in the first topic that we studied in chapter 14, there was no X's, there was no ice tables, because we knew for sure that the species completely dissociates. This is another example of a situation where the reaction goes to completion. It doesn't stop partway. See? It proceeds until one of the thing runs out.
Wait, so this only works if we have a strong substance
Yeah.
reacting with a weak, like it's like a strong base, weak
Yeah.
acid, or a strong acid, weak base.
Yes. And also strong with strong. Same thing. If you have at least one strong reactant, that's it. It goes to completion. Right? So strong species are our friends. They make calculations easy because they push the reaction to completion. Good. Okay. Yeah.
So the red is 60 millimoles.
Yeah.
So that's because the acid is 60, so it can't go past 60. That's why you need
Exactly. Yeah. So there's two things, right? Either this gets consumed fully or this gets consumed fully. If this gets consumed fully, this runs to 0. Now suppose I say that this gets consumed fully. So I put negative 150 here. By stoichiometry, I also have to put negative 150 here and positive 150 there. This becomes 0, this becomes negative. Can't do that, right? So you want to work with the smaller number. This gets a little more complicated if there are coefficients involved, and we'll do a question like that following this. But yeah, you want to consume all of the limiting reactant. That's the idea. All right, so the first case, so here's your takeaway. When the strong species is in excess, the question at equilibrium becomes a question of finding the pH due to the surviving strong species, right? If you start with strong species in excess, then the strong species dominates and you only care about the remaining strong species. That's it. So this boils down to topic 1 of chapter 14. Now let's do the other one, similarly easy. I'm going to do the same thing. NaOH plus CH3COOH gives water, and CH3COONA. This time I've reversed the roles, so this is 150. This is 60. Don't care. And 0. Once again, this is limiting 60. So minus 60, minus 60 plus 60. I'm going to ignore the units for now. 0, 90, and 60. What is this? What is this mixture that survives at the end? Strong base, weak acid, and salt. We have a mixture of the weak acid and its salt, the weak species and its salt. The salt contains the conjugate, the broken piece of the weak species. What is this combination called? What is this mixture called? We only learned one mixture before this one, which was throw out some fancy names that you've learned in this chapter at me. It will be one of them. Huh? Homogeneous, no. Homogeneous just means it's uniformly mixed. So we had weak acids, strong acids, salts, and what was the next topic? You know it. Buffers. Yes, see? Buffers. So this is what a buffer is. Buffer is a mixture of the weak species and its salt. All right, what do we do with the case of buffers? Henderson-Hasselbalch. Easy. Now, if you recall from last lecture, Henderson-Hasselbalch is a very friendly equation. You can either input in molarity or millimoles. So we don't need to convert these back to molars. We can input them directly as millimoles into Henderson-Hasselbalch. Since we have an acid and its conjugate, I'm going to use the acid Henderson-Hasselbalch equation. Conjugate divided by acid. Let me just make up some Ka. Ka for acetic acid, CH3COOH, let's say it's 10 to the negative 8, and same throughout. If Ka is 10 to the negative 8, what's pKa? 8, good. Negative log of 10 to the negative 8, right? So that's 8, plus the log of either millimoles or molarities. We have millimoles, so good to go. Conjugate, 60. Acid, 90, and you're done. That's it. Okay. Either salt, weak acid and salt, or weak base and salt. Yeah. Okay. Last question. I write down the equation. Make sure every time you write down these equations that the equation is balanced. Here, everything is in 1-to-1 ratio. It's good. But sometimes it's not going to be the case. And we'll work on an example where it's not the case. Okay. So I've given you information about CH3COOH. That is 503.3. So this is 150. I have not given you any information about NaOH. Why is that? Because that's covered here. I'm saying titrated to equivalence, meaning whatever amount of acid I have, that's going to be the same amount of base that I have. Okay? We want both of them to run out. So we start with a stoichiometric amount from the get-go. So if this is 150, in the case of equivalence, you also know what the other one is. Must also be 150 millimoles. But I should give you the volume. Let's say that the volume here is 300 milliliters. 300 milliliters of NaOH of unknown concentration, doesn't matter. We know that we should have 150 millimoles. Great. So this time the numbers are the same, so I can do negative 150, water, don't care, 0, plus 150. And so what survives at the end? Only the salt survives at the end this time, right? Well, this now boils down to the case of find pH of a salt. Remember? This is that topic now. Okay. Here, we don't have Henderson-Hasselbalch to work with, so we want to convert our millimoles directly to molarities quickly. That's 150 millimoles. What is the total volume in this question? $800 again. So it's the same number as before, 0.112. Great. So the question now is find the pH of 0.112 molar CH3COONA. This is a salt question. Recall how we do salt questions? We take our salt, we break it down into its pieces, and we only work with the one that's not neutral. CH3COO minus and Na plus. Which one is neutral here? The sodium, right? Because it came from a strong base. So this is neutral. So I'm only going to work with that part. Is that an acid or a base? It's a base, right? Because this came from a weak acid. Okay. So CH3COO minus will react with water. This is the absorbing H plus kind of base. There are two kinds of bases. Release OH minus or absorb H plus. This is the absorb H plus kind of base. This is CH3COOH. And what's left of the water is OH minus. Do I put Ka or Kb in this case? Kb, good. Ka I have given you to be 10 to the negative 8, so what's Kb? I heard the right answer somewhere. Negative 6. Yes. It's 10 to the negative 14 divided by 10 to the negative 8. Just 10 to the negative 6. Okay, good. All right, business as usual, ice table. 0.112, don't care, 0 and 0, minus x plus x plus x. And so you have x, x, and 0.112 minus x, which, so I have x squared divided by 0.112 minus x equals 10 to the negative 6. Small x approximation. X equals square root of 0.112 times 10 to the negative 6, just some number. What can I calculate using that x value? POH, good. Negative log. And so just do 14 minus to get pH. If you go back to your topic on calculating pH of a salt, this will look identical to that. Okay. Yes. Yeah.
Because I noticed in Alex, even when it's like bigger than -7, they still take the approximation.
Bigger than, yeah, so the higher the negative number, so -6, -7, -8, -9, even better.
Yeah, I mean, like even if it was like -5, they would take it.
Yeah, that's, yeah. I think even at 10 to the -4, it is okay. With like 10 to the -2, -3, it starts to become a little fishy, yeah. Yeah. Okay. All right, so once again, summary. If you start out with more strong than weak, then at the end, you only think about the leftover strong and calculate pH. Instead, if you start with more weak species than strong species, then at the end, you end up with a mixture of the weak species and its salt, which we call a buffer, Henderson-Hasselbalch. And in the last case, equivalence titration, you start with the same amounts of acid and base, and so no acid, no base survives at the end. Only salt survives at the end, so just calculate the pH of the surviving salt. Okay? All right, now let's, question? Okay. Now let's work with a question where there are coefficients, because that can sometimes trip you up. Okay. What? Oh, these were the same values, I think, as here. Oh. Yeah, okay, so adjust. Okay. Oh, I was trying to make life easy. Missed that little detail. Okay. Okay. Here's a question. Calculate the pH when 500 milliliters of 0.1 molar BaOH2 is titrated with 200 milliliters of 0.7, let's see, that's 50, 100, yeah, 0.7 molar CH3COONA. Or you know what? Let's do NH3. Oh no, we can't. I can't titrate a base with a base. Yeah, let's stick with acetic acid. Once again, Ka is 10 to the -8. Just making that up. Okay. All right. Let's write down an equation. We've got BaOH2 that combines with CH3COOH. That forms, I guess, water, because this is an OH containing base. Those usually give rise to water. And what's left here? Ba. Yeah. Oh. Should be H. Yeah, good. Yeah. Thank you. All right. Okay. Ba is a 2 plus charge. CH3CO minus is a 1 minus charge. Crisscross. You get your Ba, CH3, COO twice. That's your salt. Right? Just like what we did a couple of minutes ago. So Ba here is 2 plus. CH3 here is 1 minus. And you get that. Yeah. To the OH. The OH combined with the water to form H2O. Yeah, you're right. It's not balanced yet. Good. There should be 2 here to make it balanced, and anything else? A 2 there. So you start by figuring out the formula of the salt and then balance it later. This. Okay, cool. Here we have coefficients. Yikes. Okay, barium hydroxide, 500.1. That is, what is that? 50. This one is 140. 0. Don't care, and 0. These are in millimoles. We have to remember that. Okay. So which one's limiting here? You would think that it's 50, and you are right here, but yeah. So you got to be a little more careful. So for example, if I had made this, I'll show you. Suppose I had made this 0.6, so that this one was 120. It would still dominate. If I had made this 2 times 4, then this is 80, but now it would be limiting. Yeah. So it's not just about looking at the smaller number and thinking that that is the limiting reactant. You have to actually figure it out. So let's stick with our original thing of, what was my original thing? 7, okay. So 140. If you're in doubt, this is how you check. Assume all 50 of this reacts, okay? So this is going to be minus 50. This has a coefficient of 2, so it's going to be negative 2 times 50, right? Minus x minus 2x. Plus 2x, but don't care, and this is plus x, so plus 50. This becomes 0, that's fine. This becomes 40, it's still positive, that's fine, and this becomes 50. So it seems like we are in the green here. We got no negative millimoles at the end, so we're fine. Now let's do it the other way, just for argument's sake. Let's say that all of this gets used up. Here's how you keep track of everything. If you had written x's, you would write minus x, minus 2x, plus 2x, and plus x, right? So what I'm saying is that minus 2x is 140. So what's x? 70. This is just minus x, so this is minus 70, right? This is plus x, so this is plus 70. See what happens here? 50 minus 70, you get a negative number. That's a problem. So this is not limiting, this is limiting. But you want to do this check always when you have coefficients because the numbers can be deceptive. So make this check every time. In this case, we are okay with negative 50. Okay, so that's 0, this is 40, and 50. Great, so what is this? What case is this? Looking at what survives at the end, what case are we in? Buffers, right? This mixture is a buffer mixture. So pH equals pKa, which is 8 plus log of conjugate over base. And you have to be careful again. Your acid is 40. That's okay. Your conjugate is not 50. 50 is this guy. But each of these has 2 copies of your conjugate, right? So the conjugate is 2 times 50, which is 100. So when you have coefficients, you have to keep track of all of these little changes. Yeah. You don't care about this coefficient. That's fine. This is just part of stoichiometry, right? So you wouldn't want to multiply that 2 with this 40. You don't do that. But a subscript 2, that's different. Okay. Right, lots of things to take care of. I think that is it for chapter 14. We're officially done. This was the most important topic, so I'm glad we spent all this time on this. And let's get started with chapter 15. I promised to send you a recorded lecture last time for titrations. Couldn't do that because I was actually sick the week before my recitation. But that day I was like, I'm going to suck it up and see how it goes. So I came, I taught, and then by the end of the lecture, I had a fever again. And so I was, under the weather again. But now I'm fine this time. So since we don't have time to go over all of chapter 15, I'm going to get started with 15 and the leftover topics, this time I promise you I'll record a thing. Okay. All right. So chapter 15, same concepts, different context. In this chapter, we're looking at acids and bases doing their thing. That was our reaction. In chapter 15, the first thing that we're going to look at is dissolution, the process of dissolving. Give me some kind of solid. Some kind of solid that's partially soluble. I'll help you out. Silver chloride breaks down into its ions when you dissolve it in water into Ag plus and Cl minus. The ions are aqueous. This is solid. Right? Just a very innocent looking dissolution reaction. The K value corresponding to a dissolution reaction is called, because its solubility would be Ks, but I'll do something. Let us write down the equilibrium expression for this question here. What would it be? Products on top, Ag plus, Cl minus, and what goes on the bottom? Nothing, right? That is a product. Yeah? In fact, in every dissolution question, you'll always start with a solid that breaks up into aqueous. So the denominator will always be missing. So it's always going to be a product, not a quotient. That's why this thing is called Ks for solubility, but it's always a product, so solubility product. KSP. Just a fancy little name. Is this thing still working? Okay. There's your KSP. And here's a nice little thing. Let's give this KSP some value. I like 10 to the negative 8. I'm sticking with it. Here's a question. Find or determine the solubility of AgCl. That's the first kind of question from this chapter. Determine the solubility of X. All right, ice table. That's all I'm giving you, nothing else. The nice thing is, you can always cross out the first thing because it's a solid, right? In the beginning, nothing has dissolved, so this is 0 and 0, minus x, plus x, whatever, x and x, right? And so, x times x squared over nothing equals 10 to the negative 8. X is 10 to the negative 4 molars. That's what we have. Any questions? No. But so far so good, right? I've just done a nice ice table, nothing else. Now imagine for a second that there was something here, minus x. What that is saying is, no matter what molarity I start with, this much of it is going to dissolve, right? Because this much of it gets converted from the solid state to the ion, the dissociated ion state. So x here is indeed the solubility, but because x has units of molarity, right, big M, x is molar solubility. It's 10 to the negative 4 moles of AgCl will dissolve per liter of solution. This is molar solubility. So this question here, when they say just solubility without specifying what kind of solubility it is, what they mean is gram solubility. All that means is you want to convert this from moles per liters to grams per liters. That's a very simple unit conversion. You want to convert these moles into grams. Let's do that. 10 to the negative 4 moles of AgCl per liter of solution. I don't want to mess up the bottom. The bottom is fine. I don't want moles of AgCl. I want grams of AgCl. What goes up here? Not in numbers, in words. What goes up here? How do I make the jump from moles to grams? Molar mass. I don't know what the molar mass of Ag and Cl. Cl is 35.5. Ag is, I don't know, something. Some number, and that's it. 107. So 107 plus 35 is, I don't know, 142? 143. Thank you. Great. Moles cancel. There you have it. This is the solubility. All right, so nothing new here. It's just getting familiar with what solubility means and going from molar solubility to grams to gram solubility. Great. All right, that's the first part of this chapter. Next part. Remind me about attendance at the end of class. I always forget. Okay. Let's go back to this AGCL thing. If my Q, this is going back to chapter 13. Remember we had Q and K, reaction quotient and equilibrium constant. Q was simply not at equilibrium, the same expression calculated not at equilibrium, right? K was at equilibrium. And if you remember, Q could be one of three possible cases, right? Q could be less than K, Q could be more than K, and Q can be equal to K. Right? And in each of these cases, the value of Q determines what direction the reaction is going to move in. So, Q is less than K, means the reaction moves forward or backwards? Forward, right? Q wants to become K, so the reaction will move forward. Here, Q is higher than K, so the reaction will move backwards. And you can just not think about that for now. The reaction is already at equilibrium if Q is K. Now tell me, which direction here corresponds to formation of a solid? Exactly. Going reverse, I'm going from something that was dissolved to something that's solid, that's insoluble. So going this way is precipitation. That is horrible. Oh, how is precipitation spelled? Is it CI or CE? CI. PI. Okay. Okay. Thank you. Precipitation. So going back is precipitation. Going forward is dissolution. Great. Yes. Q was, so remember products over reactants, coefficients become powers? The molarities that you input in there, if those molarities happen to be a snapshot of the reaction when the reaction is not at equilibrium, if those values are not at equilibrium, then that's called Q. Yeah. Great. K is at equilibrium, yeah. Same thing with the values at equilibrium. Great, so in which case does precipitation happen? In which case does precipitation happen? Q greater than K, exactly. Right? So there it is. If Q is greater than K, reaction moves backwards, which is the direction of precipitation, and precipitate forms. And if Q is less than K, no precipitate forms. And here's a question. A solution is 0.5, that's fine, 0.5 molar Ag plus and 0.3 molar Cl minus. Does a precipitate form? All right, you tell me, calculate Q. Compare it with the given K, which is 10 to the negative 8, and see if a precipitate forms. Yeah. So let's put SPs under all of these guys. No overheating just yet. That's good. We're almost at the end of class. Okay, so how do I calculate QSP here? Multiply Ag plus NCl minus. Okay. This is 0.015. Or is it just 0.15? Yeah, you're right. Great. Is that bigger than 10 to the negative 8 or less than 10 to the negative 8? Much bigger, right? So does a precipitate forms or not? We're in Q greater than K case here. Yep, Q greater than K, precipitation indeed occurs. Yep, so a precipitate does form here. Okay. Is the Alex homework for this chapter already past due or something? I'm gonna shoot an email and ask him to extend it because I wasn't able to cover it last time. Yeah. Hopefully he agrees. Okay, one last question for today. No, not one last question. We have more time. Okay. Same question, but with a slight twist. 500 milliliters of a solution of a 0.01 molar NaCl solution is added to a 300 milliliters 0.02 molar AgNO3 solution. Does a precipitate form? And hint is that the KSP for AgCl is, also let me make this MgCl2. It's 10 to the negative 8. My claim is this is the same question as before, minor twist. Now, what precipitate are we even talking about here? Now you see, I began with 2 solutions. This, I said, is a solution, meaning there is no precipitate to begin with. So magnesium and chlorine, when they're with each other, they don't precipitate. That's fine. AgNO3, I've also told you that that's a solution. So this, they don't precipitate, which means that the only possibility are the cross products, right? So let's look at what the cross products are when you combine the 2 solutions. So solution 1 had, what two ions are in here? Mg, what charge? 2 plus and Cl minus, and the other solution had, well, let's forget about this. What is the charge on the polyatomic ion NO3? Nope, single minus, something to memorize. Nitrate is -1 charge, which means this should be +1 charge. Great, now let's make some cross products, because when you combine them, right? All possible pairings occur. These two are fine, these two are fine. This is question mark. And when this combines with this, it's question mark. And for this, I think you have a solubility table in your textbook or something. It's like a comprehensive table where you get to mix and match, where you see Mg with NO3, does it precipitate form or not, and so on and so forth, whether soluble or insoluble. If you do that, I think magnesium with nitrate is soluble. Magnesium nitrate is soluble, so it's not going to precipitate out. However, Ag plus and Cl minus, depending on the concentration, may or may not precipitate out. AgCl is insoluble. Okay, so we're going to look at AgCl. And another way to figure that out is look at the hint. I've given you the KSP value for AgCl and nothing else, so it's, you're looking at AgCl. Okay, cool. What is the Q for AgCl here? Just like last time, this is going to be concentration, molarity of Ag plus times Cl minus, which is what two things do I multiply here? This is a trick question. Some of you might be eyeing the 0.01 and the 0.02, and I'm unwilling to put that in for Ag plus and Cl minus molarity. What's the problem? Yeah, there are two solutions that are being combined here. The molarities that go into Q and K are the combined molarities. So you need to find the combined molarities first. All right. This guy was 500 milliliters, 0.01 molar. This was 300 milliliters, 0.02 molars. The combined solution is going to have a volume of what? 800 milliliters. 800 is becoming our favorite number real fast. Okay, and now let's work out the molarities. Let's start with Ag plus. What was its initial molarity? 0.02, right? I'm doing M1V1 equals M2V2 here. 0.02 times its initial volume, 300, equals M2, which is unknown. And what do I put here? 800, right? Combined volume. Milliliters cancel, and so M2 is, I don't know, something. Can you calculate M2 for me? Zero 0.02 times 3 divided by 8. 0.0075, thank you. Awesome, I have my Ag plus value. Now I need my Cl minus value. Similarly, again, tricky. Cl is part of MgCl2. MgCl2 has a molarity of 0.01. What is the initial molarity of Cl minus? What would it be? How many Cl's does MgCl2 break up into? 2. So if this is 0.01, what would that be? You have to double it. There's a lot of little things. So that's 0.02 to begin with. Times 500. Equals some mystery molarity times 800. What is this? Should be, no, different. 0.01? 125. Thank you. Great. What is that? Can someone calculate this last number for me?
0.00093975.
Okay, 0.4 zeros after the decimal. Yeah. 9375. Let's convert this into scientific notation so we can compare it with that. 1, 2, 3, 4, 5 hops. That's 9.375 times 10 to the negative 5. Is this number bigger than that? Bigger than KSP or smaller? Bigger, right? So does it precipitate form? Yes. Okay. So you see, there's nothing really new happening here. It's the same ice table stuff. It's, calculating quotients and whatever, comparing values. Only thing is you have to be careful with like molarities and stuff. The golden rule to remember is most of these questions demand combined molarity in the final solution. So mixing becomes an issue. You have to be careful with mixing. But other than that, this is all in the same spirit of chapter 14 and 13. Okay? All right, so that's it for today. I'm gonna finish up the rest of this chapter in a recorded lecture and send it to you guys when I can.